And I start the just I wanted to make some change in the name of the talk, because after more than 1 year, I wanted to have a different approach to what I wanted to speak about. So a new title could be a common 10 molecular ring compound, a challenging magnetic system with unusual spin 9 count state. So I will not focus always only on Newton scattering. Let's see if I can just, okay, that's right. Well, I want to speak about the family of compounds, in particular, one of the members of the family. This family has been known for 15 years, and it's made of 10 common chromium ions that are connected by different ligands. Some ligands are inside the ring, and others are outside the ring. And sorry, I wanted to go back. Okay, that's right. Okay, here's the laser. Right. So there are two types of ligands. As I said, some are inside, the others are outside, and this changes a lot the magnetic properties of these rings. These rings are almost planar, which makes them suitable for deposition on substrates. Actually, we have done some experiments making the position of one of the members of the family on surfaces, but I'm not going to speak about this in this talk. Maybe in the next conference, I could just include these, speak about these things. And there are types of wheels made of chromium and iron. Here you have some examples, and all these examples here are antiferromagnetic, so the total spin is 0. When just changing the ligands, we change the angles between the neighboring chromium atoms, ions, and through these the exchange interactions through two oxygen atoms, and so the molecule in general has a symmetry, which is close to a D5D symmetry, but it is actually Ci. That means it only has inversion symmetry. And the symmetric unit is formed by 5 chromium, so the other 5 chromium atoms are obtained by inversion. So I will work with 5 actually, and then the rest of the ring is obtained by inversion. So depending on these two types of ligand, we have different results. These results, I start with just this ring inside, okay, which is the ethyl group, and here we have 5 of the 6 members, and these 2 members show susceptibility that corresponds to a completely antiferromagnetic ordering of the spins around the ring, and so the total spin is 0. This is very clear here in this case. And the thing is that when we just change the same the ligand at the same position, instead of the ethyl group, the methyl group, what we have is a fully ferromagnetic case. This is ferromagnetic even if, because it has a positive Curie temperature, and this drop at very low temperature has been assigned to antiferromagnetic interactions between molecules, between wheels of 10 chromium spins. However, when we change the different action two types of cases, and the difference between these two correspond to changing the other ligand. And now, even with the methyl group that I have just shown as antiferromagnetic, when we have these larger ligands, so that the ring is a little bit larger and the distance between molecules is also larger, what we have is a clear ferromagnetic interaction along the ring, but the unusual behavior is that when we measure something like this, what we get, and this is magnetization on the left, and this is susceptibility times temperature on the right, and this is the magnetization along a direction perpendicular to the chromium-10 plane, and in red, this dot here, this is magnetization in a direction in the plane of the ring. What we get is something that is compatible with the spin 9. Spin 9, with respect to the totally ferromagnetic case, which is spin 15, means that some antiferromagnetic interactions have to be considered in this case. So this makes a completely different case, which is usually in rings when we have typically or all ferromagnetic or all antiferromagnetic, and here we have important antiferromagnetic interactions inside the ring. So now when we see how we go to next, right? The spin 9 ground state was also confirmed by EPR experiments when these compounds were synthesized. And so there were the installations that were well compatible with this spin 9 ground state, and the evolution of the EPR spectrum with temperature were interpreted as having a first excited state with spin 10, so that what we would have is something like this, with two opposite ions or spins in a different directions, or antiferromagnetically coupled to their neighbors, and they are just situated or located in opposite positions because of the inversion symmetry. And moreover, the anisotropy, this single anisotropy, molecular anisotropy, magnetic anisotropy, was also compatible with a direction which is perpendicular to the ring plane. And the geomagnetic factor and the value of this interactive anisotropy parameter was determined from those experiments. So this was just a suggestion, and so we wanted to try to get evidence of more direct evidence of this scenario, this picture, and so we needed an experimental energy spectrum, and that's why we chose to obtain inelastic Newton scattering spectra. So we chose for that member of the series to measure on the LET spectrometer at ICES. This has a high resolution. Actually, we measured with an incident energy of 1.5 milliradian volt, and we can get an elasticity resolution which is better than 20 micro eV. So we are actually what we want to see is low energy peaks. We could only use a molecule with hydrogen. We could not get a saturated sample. That means that we have a large component, a large elastic peak coming from over hydrogen, and then it actually has been hard to get information from it, but we got it, and that's what I'm going to show you immediately. This is the spectrum taken at 1.8 Kelvin, and so we have systems excitations. This is systems de-excitations on the left, excitations on the right, but I'm going to work on this part of the spectrum. And so we see a small bump just close or nearly inside the elastic peak, and some other features at different energies around 0.5, 0.445 and 0.8 millielectron volt. Now, how can we get information from this? First, we have to check that this peaks or these excitations here are magnetic and not have something to do with elastic or vibrations in the system. So, in order to get that, we have to try to extract and to subtract the elastic peak, and for that, what we did is just we took a 5 in a spectrum in the 5 Kelvin. Since we are at this more or less take the relationship between a millielectron volt and Kelvin, and 1 millielectron volt is 11.6 Kelvin. So we are. This is really corresponding to a very low temperature. So at 5 Kelvin, most of the states involved here are mostly occupied. So what we see here is something, the very low the very low energy is almost absent in the excitations are almost absent in the 5K spectrum, right? So to get information from these parts, we use this spectrum, and what we get is this. So this is close to the elastic peak. So we see not only one peak from that small bump, but 2 peaks. And so in order to identify them as magnetic excitations from the ground state, and having in mind that the elastic Newton scattering selection rule of change in spin 0 plus minus 1 and change in the Z component of the spin 0 plus minus 1, what we have, we can use this integrated intensity and energy for a particular value of the momentum transfer, and what we get is this dependence. These lines are just guide to the eyes. It's not a natural fit at all, but we have completely different behavior. These behaviors are compatible with vibrations or photons and so on, but they are compatible with magnetic excitations in 2 different cases. In this one, when we have that for vanishing momentum transfer, we have a finite value of integrated intensity that is consistent with magnetic transition, magnetic excitation without the change in the spin, while when we have this other case, which is goes to 0 for vanishing momentum transfer, we get something consistent with the change in spin. Now, if we want to calculate these obtained parameters from this spectrum, then we should have something like this. So I put it in the Hamiltonian with the Heisenberg term, and just this is just to make clear that we have to close the ring, and then we just put in uniaxial anisotropy interaction. But if we want to solve this with this Hamiltonian with the spin 3½ for each chromium spin, then we have more than 1 million states. So we need some strategies to solve this problem, because this is not possible to do it completely. So what we can do is to use a strong limit approximation. This has been very usual, mainly when you have the extent interactions are much larger than the anisotropy constants. And in this case, we block diagonalize for total spin s, and assuming that we have no anisotropy, and then we have somehow the anisotropy of the full ring just by calculation or experimental determination, and from that then we can calculate the modification of the energy. So we could try to solve this with in a simple case, that means d equals 0, which can be block diagonalized, and then the computing work is much easier, and then we add this as calculation. The other thing is the possibilities when it is not sensible, because we are not sure to be that this is fulfilled. Then what we can do is we can still block diagonalize the total spin when possible, and calculate the anisotropies of each spin. The problem is that we have very large matrices here, and even for the case for this for any of the cases. So what we do is we fully diagonalize in the case of not very large matrices, and we use sparse diagonalization for larger matrices. But in order to compare or to get a spectrum, we have to start from a good set or sensible set of exchange parameters, and then we can try to get some hint from ab initio estimates. For this, this can be very reliable, but not so reliable for the exchange. So now I want just to note that here we have the angular dependence of the chromium along the angle chromium oxygen chromium along the ring with two different. One is the inner and the outer angle, and when we calculate the exchange energy, we see something like this, right? So it is important to note that we have an exchange constant that follow the same tendencies that the angles. Now, how can we get this? This is just the set that we want to check that it works. Well, the ab initio values don't work. Unfortunately, they don't work. So what we can do is use something different. We use these two sets of experimental results, associability and magnetization, and we try to fit somehow the curves using Monte Carlo simulations. We can use classical Monte Carlo simulations for high temperatures using the classical spin 3½, or we can use Monte Carlo calculations, quantum Monte Carlo calculations for low temperature. But in this case, we can only have the component parallel to the perpendicular to the chromium 10 plane, and that means parallel to the anisotropy axis. because the other component has what is called in quantum Monte Carlo simulation the sign problem. And so we could get something like this, which is fairly good for the magnetization. So we have more or less going in the right direction, and low fields we also have a good agreement with magnetization, but it's not so good and high magnetic fields. In any case, this set of parameters seem to simulate more or less correctly the macroscopic magnetic measurements. What is important is that here the ab initio calculations predicted an asymmetry around the chromium-3, what we called one of them, chromium-3 atom, and we also needed this for the calculation. When this asymmetry is not used, then the agreement is much worse. So we can calculate now the elastic Newton spectrum. So just to clarify how it works, I have just put this, which is without anisotropy.
We have 1 minute.
1 minute. Okay. Okay. So these are the states, the control spin, and when we add an anisotropy at this site, which is derived from the total anisotropy, which can be done in the strong interaction in exchange case, then we get all this spectrum where we can see some of the arrows just show what can be seen in an elastic Newton spectrum, right? So from here we can calculate what happens with this state, and we calculate with this value which is close to that predicted by EPR. We have this. We can even introduce a small rhombic term. So this state corresponds to what is the splitting by anisotropy of the ground state. And now we can go to this one, which is a change in delta S. That means that it goes from total spin 9 and total spin 8, and not total spin 10 as suggested by EPR. So now we have not much more, because here we have more peaks, but these peaks are also observed here in the calculations with those set of parameters obtained from the susceptibility and magnetization. So this structure here comes from excitation from the ground state to this set of states, and maybe, so here it's not so clear, but here we have two higher states. All these here have not been calculated, but they are not accessible by elastic Newton scattering, so we don't care about all this part because we cannot see it with that. And so finally, so we can see also from elastic Newton scattering the ground states the multiplet of spin 9, total spin 9, but the lower state, the lower excited state are spin 8 multiplets, not spin 10 multiplets as previously claimed. And we can see maybe some other possibility, other configurations of about 10 Kelvin that are compatible with EPR. We have to change a little bit the anisotropy, the molecular anisotropy constant as previously claimed by EPR. It's important to note that we need some asymmetric interactions around one of the chromium atoms, which is particular inside the ring. And the important thing is, so that exact molecular symmetry has to be taken into account. The approximate D5D symmetry is not, we would not give good results. And so we see that intramolecular many spin specs which are reflected in the spectrum, because we can see the different types of the different states with different spin. And But here you can see an example of how the
we are
this pattern.
Javier, we're out of time.
Okay, so it can be. So that's all. So the approximation we have done is to have a manageable and still comprehensive approach. And so the people involved here, thank you for your attention. Group in Zaragoza, two groups in Italy, and Tatiana Guidi in the facility in the UK. Thank you.
Okay.